Hi again. So in this video, we're going to look at another problem of eigenvalues and eigenvectors. And in this case, we're going to look at the eigenvalues and eigenvectors of van der Monde matrices. And that's a question that's been asked during a test in February 2024. And just to fix ideas, van der Monde matrices are matrices that are written in a format similar to this. So for instance, what you see here on the left is an example of a van der Monde matrix for n is equal to 4, and another one on the right for n is equal to 2. All right, n is equal to 2 is the only particular case that we're going to consider in this video. But everything we do here can be expanded to any value of n. And actually, the question that was asked during the test started first with n is equal to 2, and then there was a question about, okay, how does it expand when n grows and becomes anything? All right, this second question is a little bit more difficult, and I'm not planning to deal with the second question in this video. And so instead, we're going to look at the problem with two perspectives. The first one is the use of the characteristic polynomial, and the second one is the use of the general method, keeping in mind that we are solving eigenvalues of a matrix that in principle has any possible size. All right, so what I should mention at the same time is, and that's a condition of this question here, is that all AIs are small numbers. All right, so all AIs have order of magnitude, let's say epsilon, which is much smaller than 1. All right, for any I equal to 1 until n. All right, but though the only case we're going to consider is a case when n is equal to 2. And of course, I'm just planning to use this exercise here to show you that no matter the method you use, you should obtain the same results. All right, so let's see how we can proceed with this exercise. Okay, first thing, there's no epsilon in the statement, as you might notice, right? There's no epsilon here, and we can introduce, of course, epsilons because we have been notified that all alpha entering in the composition of that matrix are small numbers. All right, so let's introduce small numbers, rescaled values for A. Let me just call them alpha tilde probably. Let's introduce alpha i's. I is running from 1 to n. Which are all of them of order 1, and such that alpha I is equal to epsilon time alpha I tilde. All right, so we have a rescaled version of the small numbers. All right, alpha I, we said, is of order epsilon, and the alpha I tilde is of order 1. All right, so the matrix that we want to solve is M or M2. When n is equal to 2 is 1, then epsilon alpha 1, 1, epsilon alpha 2. All right, so we're going first to use the characteristic polynomial for this matrix in order to determine the eigenvalues. All right, so we need to write the determinant of m minus lambda I. So basically what we just do here is we subtract lambda from the diagonal elements, cancel this determinant, and this provide the characteristic polynomial. All right, so we see here we have a lambda square, then minus 1 and epsilon alpha 2 tilde times lambda, and then minus epsilon alpha 1. All right, multiplied by alpha 1. And I forgot, of course, plus epsilon alpha 2 tilde coming from here. All right. So we need to find the roots of this polynomial here. Let's try with a regular ansatz. Try with regular ansatz. And if it doesn't work, we'll try something more refined. What I forgot to say, is that we were asked to determine the eigenvalues and eigenvectors. Eigenvalues and eigenvectors up to order epsilon. Up to order epsilon. Okay, so it means you're not asked, when you see this in a question or in a statement, you're not requested to go beyond order epsilon. So you're not requested to get, for instance, terms that could be of order epsilon square. All right, so we're going to try a solution of this problem with a regular ansatz, and we're just going to write lambda is lambda 0 plus epsilon lambda 1 plus things that are order epsilon square, and which we don't really care about because of what's been asked. All right. So if we substitute this in the polynomial, we end up with lambda 0 square plus twice lambda 0 lambda 1 plus order epsilon square. All right. This is for the first term. Then we have minus 1 plus epsilon alpha tilde 2 lambda 0 epsilon lambda 1 minus, or let's say plus, alpha 2 tilde minus alpha 1 multiplied by epsilon. And this, I dropped already a term that is of order epsilon square, so let me just write it like this. All right, so I think we are in a position now to write the governing equations at each order. And so at leading, we have, of course, I guess I forgot to write epsilon here. So you see, when this is something usual, you notice right away where a few terms or a few mistakes are made. Then at leading, what we have is lambda 0 square minus lambda 0 is equal to 0, meaning that we have two roots at leading order. Lambda 0 is equal to 1 and lambda 0 is equal to 0. And at the following order, epsilon, what we have is just what remains. So 2 lambda 0 lambda 1. We have here, I see a minus alpha 2 tilde lambda 0. Then I see a minus lambda 1. Then another epsilon square, which is dropped. And then plus alpha 2 minus alpha 1. And this is equal to 0. All right, so we have two roots, 1 and 2. And then when we substitute them in the second equation, let's probably try to isolate lambda so we can get a generic equation that can be used for the two roots at the same time. So we have 2 lambda 0 minus 1 multiplied by lambda 1 is alpha 2 tilde lambda 0 minus alpha 2 tilde plus alpha 1. All right, so when lambda 0 is equal to 0, we see that we have lambda 1. The left-hand side here is minus 1. This disappears, and so alpha 1 is just the opposite of the right-hand side. So this is just alpha 2 tilde minus alpha 1. And when lambda 0 is equal to 1, the left-hand side here, 2 minus 1, the left-hand side is equal to 1. And here we have alpha 2 minus alpha 2. So what just remains is alpha 1 tilde. So in that case, lambda 1 is alpha 1 tilde. All right, and so we have, I should probably have swapped them or used different colors so that we are sure we don't mix them. All right, like this, and like that. All right, so just to summarize, we have two roots. We have the two eigenvalues. Lambda, let me just call it lambda A, is in gray first, so lambda 0, which is 1, plus epsilon alpha 1 tilde. And we have lambda B in yellow, which is 0 plus alpha 2 tilde minus alpha 1 tilde multiplied by epsilon. All right. And so you see it in the statement. I didn't want to say keep two terms in the expansion. That's maybe just a notice for those of you who might watch this video and get ideas for probably your own test questions. I didn't want to say keep two terms because otherwise it would have forced the persons who are trained or tested here to go up to the next order. And this actually makes things a little bit more difficult in this exercise. So I didn't want to go there. Okay. We could try to determine the corresponding eigenvectors, all right, which is something that is also possible, although this is only feasible, I would say, when we don't have too many terms in the expressions we keep for the eigenvalues. All right, but let's try to see how we can do this. Eigenvectors. I should also say that this approach here is not really elegant, and you would definitely prefer the general method to determine the eigenvectors. All right. Use general method instead. And general method is treated in step number 2. Okay, so we'll carry the different steps related to the general method in a few moments. All right, so meanwhile, how do we determine eigenvectors associated with eigenvalues? We just subtract the eigenvalue we have from the diagonal elements. So somehow we just replace lambda here by first lambda A and then lambda B, and determine the corresponding eigenvectors. All right, so let's consider first lambda A. So the problem we want to solve is 1 minus lambda A. So that's 1 minus 1 minus alpha epsilon alpha 1 tilde. We have epsilon alpha 1 tilde. And then in the second line, we have 1 and epsilon alpha 2 tilde minus 1 and minus epsilon alpha 1 tilde. All right, and this multiplied by the first eigenvector, I could probably write it phi 1 or phi A should be equal to 0. All right, and this is an eigenvector. All right, so one way to solve, well, in principle, you could use the first or the second line, and that should provide the same results. So if I decide here to use the second line, all right, and if I use a unit component as the second entry in the eigenvector, so if I just choose phi A in the form something times 1, I see that this something actually is nothing but the opposite of this number. All right, so that's 1 minus epsilon alpha 2 minus alpha 1. So that indeed when I compute the product of the matrix that is here and this vector, you see that the second line provides 0. We can also check what the first line would give. First line, so I just compute the product of the first line and the eigenvector. That's epsilon alpha 1 tilde multiplied by 1 minus epsilon alpha 2 tilde minus alpha 1. There is a minus over here, plus epsilon alpha 1 tilde multiplied by 1. And so what we have here, you see that this disappears with that, and we have indeed something that is of order epsilon square. All right, which is anyway the order of magnitude of the terms that we have discarded here, because of this. All right, because lambda a was accurate up to order epsilon square. All right, and so you see here, why did I use the second equation in order to determine the eigenvector? I use the second equation because the first line is of order epsilon here. And so I couldn't be really accurate with using only the first equation, which, by the way, would just have said that the second component is equal to the first component. And this is something that I have indeed right. So second is equal to first, but only at leading order, not including terms of order epsilon here, which cannot be captured by the first line, okay, product with the first line, because those are small numbers, all right? You see that the second line is of order 1, and this is why the second line needs to be used in order to determine the eigenvector. All right, so that's something very important, so keep this in mind. I'm going to highlight this so that we remember this is wrong and this is right, okay? And so this is certainly different from 1 and 1 at leading. At leading plus the first correction, so up to order epsilon. All right, good with this. Then what could we say? Let's go for the second eigenvector. Second eigenvector, we need to subtract from the matrix. Let me just copy it so we have it next to the workspace. Copy this and paste. So we need to subtract now from the diagonal lambda given by this expression here. So we have 1 minus alpha 2 tilde minus alpha 1 tilde. And then we have epsilon alpha 1 tilde. Then we have 1 epsilon alpha 2 minus epsilon alpha 2, so they disappear, and then we have plus epsilon alpha 1. This multiplied by the second eigenvector should be equal to 0. All right, like this. So we have to solve that equation. And so to make it simple, I would say let's use again the second line of the matrix, because at least we see we have something of order 1 over there. Doesn't matter so much that we don't have order 1 here. What matters is that we have order 1 after completion of the full product, all right, of the second line by the first line. And so for instance here, if I want to again use a unit entry on the second component of this matrix, which seems to be quite easy. The first is just minus epsilon alpha 1 tilde. All right, and so here we are. Okay, so in summary, we have in yellow, that is lambda b, which is 0 plus alpha 2 tilde minus alpha 1 times epsilon. And this comes with this eigenvector. And in gray, we had lambda 1, which is 1 plus alpha tilde epsilon. And this one comes with the eigenvector over here, like this. All right. Okay, at some point we know we'll have to determine the left eigenvectors, but that's probably something we can leave for the next step. Okay, so we can consider that the problem now is solved. I don't know how much time we took to do this, but definitely you see that was not too difficult. All right, let's try to see now with a second approach, which is the general method. All right, and so for this, we want to determine the eigenvalues and the eigenvectors of, again, the same matrix, M, this one. And to make it convenient, you might have understood from previous videos that I like to rewrite M in a more generic format. In this case, we only have terms of order 1 and epsilon, so I can just rewrite it this way, where M0 is this matrix. At the same time, it just gives you a better view on how the unperturbed problem is and how the perturbations enter in the problem. All right, so we see that in this case, both matrices are singular. All right, and that's something we noticed, all right, because there's at least one eigenvalue that is equal to 0. So it means that at leading, the unperturbed problem is involves already a singular matrix. That's what we see here. And in the general approach, you remember that what we want to do is to introduce ansatz for both eigenvalues and eigenvectors. All right, so I'm going to use this ansatz for the eigenvalues, and I will use this ansatz phi 0 plus epsilon phi 1 and so forth for the eigenvectors. Okay, these are eigenvectors. And so if you substitute this into the governing equation, what we have is when we just write that m minus lambda I times phi is equal to 0. So that's the eigenvalue problem, or the governing equation somehow, eigenvalue problem. We have, let's just replace m by the sum of m0 and epsilon m1. Lambda is lambda 0 plus epsilon lambda 1 multiplied by identity matrix, and this is equal to phi 0, multiplied by phi 0 plus epsilon phi 1, and this is equal to order epsilon square. All right, so now if we distribute everything, what we have is m, let me just first probably collect the different terms. All right, so we have m0 minus lambda 0 I, then epsilon times m1 minus lambda 1 I, and this is all multiplied by phi 0 plus epsilon phi 1. All right, so at the end, it's not so difficult, right? We have the leading order here, all right, which also corresponds to the unperturbed problem as expected. Then we have plus m0 minus lambda 0, 1, I phi 1, and m1 minus lambda 1 times phi 0. All right, so at leading order, we need to solve this. And the next order will be same operator applied to phi 1 is equal to minus m1 minus lambda 1I times phi 0. All right. And so we start with the leading order first. Leading or unperturbed if you want. All right. So what do we have? m0 minus lambda I. So m0, let's come back to m0. This is 1 minus lambda 0. We have 0. We have 1 and minus lambda 0. Multiplied by phi 0 is equal to 0. So we need to determine the eigenvalues by solving the determinant, which is something very similar to what we had earlier expected, except the epsilon alpha 1 tilde and epsilon alpha 2 tilde, all right, because we are in the unperturbed problem. So that's even much simpler. In fact, the unperturbed problem, the perturbed problem that we solved earlier in the first approach was not too tough in this case, which makes this problem quite easy to solve, even almost explicitly, of course, or exactly. So that's what we have. This determinant is equal to 0. And so again, of course, we recover lambda A, the first one, is equal to 1, and lambda B is equal to 0. All right, that's at leading. Lambda A, I'll just use the same color code, is in gray, and lambda B is in yellow. All right, so same and same. All right, once this is done, we can get the eigenvectors at leading. Okay, and this is where it is a little bit more elegant, I would say. So eigenvectors in the first case are obtained just by subtracting lambda A from the diagonal elements. So we end up with a matrix that is exactly like this, multiplied by phi 0 A is equal to 0. And so we need to use the second equation here. You see the first one is useless. And this corresponds to what I discussed over here. All right, you see clearly that in the unperturbed case, this disappears. And so we are just left with 1 and 1. All right, so the first equation actually can even not be used in this case. All right, and so that's clear, and this is also why perturbation methods are great in this sense, because they tell you just what you can and what you can't do. So what we obtain for the leading order solution for the eigenvector is this one. Then let's go to the next order, and if we go to the next order, we need now to subtract 0 from the diagonal. So we have another matrix which is like this, 1, 0, 1, 0, multiplied by phi 0 B. And so phi 0 B, this product needs to cancel. Is equal to anything 1 multiplied by 0 plus anything for the second component. Okay, so let me just use 1 I could basically here use 2, 3, 4, whatever I want, even I or -5, because this is a quantity that is multiplied by 0 no matter the line you consider. By the way, both of them are exactly the same. All right, so we have the two eigenvectors here. Okay, so then probably could be good to have a quick look at the left eigenvectors. All right, so this is maybe the right moment to do so, because we know we're going to need them. And why will we need them? Because we see that the matrix here is non-symmetric. You see, this one is non-symmetric because we have 0 and 1 over here, and this means that in order to get rid of this by projection on something, we have to project on the left eigenvector and not on the right eigenvector. All right, so this is just the right moment to look at the left eigenvectors. And so we have the same problem here, except that we want to write, let me just call them psi, for instance, psi 0a transposed. It is a left eigenvector multiplied by 0, 0, and 1 minus 1. And this should be equal to 0. All right, so you see that the vector that we need to use in that case is equal to whatever you want, and then 0. All right, so use whichever column you want in this case. All right, the two columns provide the same information, so use, for instance, the first column here, and you see that 1, 0 transposed times 0, 1 is indeed equal to 0. All right, or seen differently, these are two orthogonal vectors. And then what we have for the second, psi 0b transposed multiplied by 1, 0, 1, 0. All right, this should be equal to 0. And then it means that psi 0b, you see again that no matter, the second column here is completely useless, so we need to use the first column. And so the vector that is orthogonal to 1, 1 is just 1 and minus 1. All right. Okay, this solves completely the leading, so now we can just have a look at the first correction. First correction. All right, so the first correction, we proceed right on. I think this is something we did already a few times in the previous videos. So we proceed right on with the projection on the left eigenvectors, just to get rid on the left-hand side in that equation. So projection on the left eigenvectors provides 0 on the left-hand side is equal to minus psi 0 transposed. Can be either A or B, all right? What I'm just writing here is valid no matter whether you're looking at the root A or root B, times M1. Or let me just expand this, times phi 0 plus lambda 1 times psi 0 transposed times identity matrix here. All right, but it comes just between two vectors, so it can just disappear. And so if I just write the equation with the different sizes of vectors and matrices, that's what we get. And so then definitely we can obtain lambda 1. So the first correction to the eigenvalue from there, lambda 1 is equal to psi 0 transposed M1 times phi 0 over psi0 transposed and phi 0. All right, so what we just have to do now is to compute those products for A and B, and that will just be it. All right, so A, psi0 A transposed. Okay, psi0 transposed M1 phi 0. This is 1, 0 multiplied by M1 was introduced earlier over here. All right, this is now that alpha I and alpha 1 and alpha 2 enter into the picture. Alpha 1, alpha 2, and this needs to be multiplied by phi 0, which is 1, 1. All right, this is 1, 0 multiplied by alpha 1 and alpha 2, and this is alpha 1 tilde. That's for the numerator. Denominator, we have 1, 0 and 1, 1. This is equal to 1. Okay, it means that lambda 1a is equal to alpha 1 tilde. And that's the first correction to the eigenvalue. All right, we can check that this value is similar, is identical, not similar, is even identical to what we got before. Exactly, you see here, 1 plus epsilon alpha 1 tilde. All right, so we are good to go with the following, which is B, and then B is psi transposed M1 phi 0. That is 1 minus 1 multiplied by alpha 1, 0, alpha 2 tilde, and then multiplied by phi 0, which is 0, 1. So we have 1 minus 1 multiplied by alpha 1 tilde and alpha 2 tilde. So we have alpha 2 minus alpha 1. And denominator, psi transposed times phi. It is 1 minus 1 times 0 and 1. This is minus 1. All right, so it means that lambda 1, B, is equal to negative alpha 2 minus alpha 1. So this is alpha 1 minus alpha 2. All right, we will check. This should be in yellow over there. Oops, alpha 2 minus alpha 1. Let me just have a quick check. Might have been something wrong. Pop, 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 pop. Psi transposed phi 0 is minus 1. Seems alright. And psi transpose, you might be on the opposite side of the screen and probably have found, if you're doing this at the same time as me, of course, I just don't know why I wrote alpha 2 minus alpha 1 here, all right, because this is alpha 1 minus alpha 2. Clearly it's obvious. I'm sorry for that. I'm sorry for this. So this is alpha 2 minus alpha 1. All right, this is where I was wrong. And so definitely what we have here is fine. And this is alpha 2 minus alpha 1. All right. So, well, in summary, I could just copy the same summary as the one we had earlier, but you see that we have the two eigenvalues, which are these. We got the leading already for the eigenvectors. All right, so we found already 1, 1, and we found 0, 1 for phi b. All right, we found 1, 1 for a. Sorry, 1, 1 and 0, 1 for b. And for A, okay, 1, 1 for A, and 0, 1 for B. Let's see now if we can get the first correction here using the general method. Okay, and so to get this, to do this, what we need to do is to come back to the equation we want to solve at the next order, which is that equation, right? So we know that this matrix is singular. That's something we get. We could compute now lambda 1 by projecting this equation on the left eigenvector of this singular matrix. All right, so we are sure that on the right-hand side, there is no component in the direction of this eigenvector. And now we can just solve this equation in order to determine phi 1, at least up to a certain constant, which is proportional to the leading order over there. All right, so I need to copy this, and the last step will be to solve this in order to get the eigenvectors. All right, so eigenvectors. We come back to that. So let's consider the first one. M0 minus lambda 0 I is this matrix here. All right. This is how we wrote it earlier. All right. So I'm just going to use here this arrow to remember we start from there, either from here, either from there, when we'll be considering later B. All right, so we have 0, 0, 1 minus 1. 0, 0, 1 minus 1 times phi 1. And this is equal to minus M1, which is this here, multiplied by lambda 1 times I, and lambda 1 is lambda 1a, so we have minus alpha 1, alpha 1, alpha 2 minus alpha 1, and 0, and this should be multiplied by phi 0, which is 1, 1, phi 0, 0a. All right, so we have minus 0, which is definitely good, right? Because we have 0 on the left, so we should have 0 on the right. If that would not be the case, then we would have had a problem. And then the second line provides just alpha 2 minus alpha 1 here, but I will incorporate the minus sign, so we have alpha 1 minus alpha 2. All right, and so we can choose for phi 1. We can choose, for instance, we see that we have 1 minus 1. I'm going to use the second line. All right, so first entry minus the second is equal to alpha 1 minus alpha 1 tilde minus alpha 2 over there. All right, this times phi 1 is equal to alpha 1 minus alpha 2. And so maybe we can just to make sure we end up with the same solution as we had before. You see we used here alpha 1 minus alpha 2 and 0, which is something fine, of course. So we'll have phi 1a. Phi 1a is alpha 1 minus alpha 2 and 0 plus any arbitrary constant multiplied by phi 0a, which is 1, 1. 1, 1. Okay, in particular, we can choose k is equal to 0. All right. And doing this, of course, this is why I was looking at what we had earlier. We obtained the same expression or the same formulation as what we had before. Okay, then let's go to the second equation, b. Okay, this is the last one. So now the left-hand side matrix, I go back to this red arrow. We have 1, 1 and 0, 0 in the two columns. So 1, 1, 0, 0. This should be multiplied by phi 1b, the correction to the second eigenvector is equal to minus. All right, now we need to subtract from m1, which is down here. We need to subtract lambda 1b from the diagonal elements. So we have alpha 1 minus alpha 2. We have here alpha 1. We still have 0 over there. And we need to subtract from alpha 2, we subtract alpha 2 minus alpha 1. So what remains is alpha 1 tilde. And this needs to be multiplied by phi 0b, which is in yellow up there. So this is 0 and 1. All right. So we obtain alpha 1 and minus alpha 1 and minus alpha 1. Okay, let's write it like this. This is more clear. All right, so we see that, of course, the two lines provide the same information, and if that was not the case, again, it would be a problem. All right, so choose whichever line you prefer, and it just says that something times the first component plus anything times the second, 0 times the second, which could be anything, and this is equal to alpha 1. All right, so it means that the first component here of phi 1b is minus alpha 1 tilde, and anything for the second component. So for instance, I could choose 0 plus any arbitrary constant times the eigenvector, which is k times 0, 1, and you see indeed that it provides something like this. All right, so in particular, if we choose, we can choose k is equal to 0, and if we do this, then this term disappears, and the first correction is minus alpha 1 tilde, which should be compared to minus alpha 1 tilde. All right, which is the same solution as the one we had with a generic approach. All right, so this example here was just, this exercise was just here to show you that we have two different approaches to solve the same problem. Of course, in this test question, you were asked to go a little bit higher than just n is equal to 2. You could go to n is equal to 3 or 4. That's why you have 2 hours to complete this this problem. You see the problem, in fact, if you try to solve it for n is equal to 3 or 4, becomes a little bit more nasty because there might be singularity issues when alpha 3 is not strictly related to alpha 1 and alpha 2. That's something you can try if you wish. Well, if not, this is probably a little bit too technical here to address in a short video. And that will probably be the topic for another isolated video. All right, so I hope you understood in this case that the problem was not too tough. You realize that first writing the characteristic polynomial here, there is no small number here multiplying the highest power in lambda, so the lambda square, which means that we do expect regular expansions do the work. It means that there is no large root. Okay, there might be a root equal to 0, that's not an issue, but at least there is no large roots. All right. It also means that when you look at the unperturbed problem here, you still have 2 roots, 1 and 2. Okay, nothing is to be expected as a very large root. This is quite convenient, and this is typically something you would observe every time you look at eigenvalue and eigenvectors of the classical problem. The classical problem is when there is just one matrix and you solve this matrix minus lambda I. All right. You can also keep in mind that if the unperturbed problem, in the unperturbed problem, matrix is M is already singular, which is the case here. You see in the unperturbed, this is 0, 0, and this is singular. You should, of course, expect at least 1, 0 eigenvalue. All right. Nothing really specific here. That approach for the eigenvectors, I say, was not really elegant. This is something that could be feasible here. And I think we were quite lucky to find expressions that are quite short and easy to write. That wouldn't be the case if you start looking at problems which are, for instance, 3 by 3 or even more. All right. For this, you should definitely prefer the general approach. In the general approach, I just remind you that this notation here is something that is quite useful and typically shortens the following notations, especially those. It makes it possible for you to write a simple expression for the first correction. That's an expression you find in many, also in many scientific publications, something that looks definitely like this, which corresponds to a first correction. So I would just highly recommend that you do the same because it simplifies equations and makes them a little bit more general. All right. So I hope you enjoyed and you understood everything in this video, and well, keep going with watching the other videos. Thank you.